d square t by dy square plus mu by k du by dy whole square equal to 0. How did you get that term? From the phi term. You have the phi term with you. In that, if you look at the phi, you have the phi term with you or no? So if you look at that, all del by del x terms vanish, del by del z terms vanish, v terms vanish, w terms vanish. All you have is from that second del u by del y plus del v by del x whole square. From that particular term del u by del y whole square remains. So now look at the expression, now the energy equation, the entire set. Now all of them actually are ordinary differential equations. This is point number 1 you should notice, observe, appreciate. A complete set of nonlinear partial differential equations in its entirety by, in this particular case of this particular physical model we have taken, with certain fairly reasonable, acceptable, justifiable assumptions, it is brought down to the simplest. We cannot get anything more simpler than this in convection. And dv by dy equal to 0 says v equal to 0, the solution is already there with the boundary conditions, of course. D square u by dy square equal to 0 remains. The y component is a hydrostatic pressure description. W is 0 everywhere, and then you are only 2 terms in the energy equation. So now you can change all the dou u by dy, dou t by dy to simply du by dy, dt by dy, number 1. This actually tells you how, before you formulate during the formulation of the problem, you think what assumptions are justifiable. That's the first thing you should there is no necessity for directly hitting the complex partial differential equations. Also please understand, these were all done when there were no computers. They said, how do we simplify the problem for our hand calculations? Computers came in only in the 40s, early 40s, during the Second World War. It was basically developed by the Manhattan Project, basically the nuclear project. Before that, what were they doing? And also that was the time when heat transfer was really picking up. Heat transfer as a subject to be taught in colleges came only in the 1960s actually. If you look at the first book by Jacob Hawkins, 1955 or so, that is the very first textbook for heat transfer. People didn't know what to put into that. Later it has now come to the Incropera, Dewitt and Bejan level actually. So making assumptions, simplifications was a necessity at that time, and this apparently simple problem you can make it into a 3-dimensional thing. If you do not put in that del by del x tends to 0, del by del z tends to 0, it becomes a right solution starting from the leading edge to the trailing edge and the two sides. What you have done is, I will not worry about the flow near the edges. Always you see, even when you do the experiments, you will see near the edges you will have 2-dimensionality, 3-dimensionality. What do you think is a 1-dimensional flow? There will be 2-dimensionality. What you think is a 2-dimensional flow is a 3-dimensionality. And boundary layer assumptions are not valid very close to the leading edge, as all of you know. There are certain complications, both physical and mathematical. So first takeaway from, as far as I am concerned, is first of all the procedure of a convection problem starting from the physical model. The second takeaway is, how do I simplify before I start solving? Now you have computers and codes, so you write down the, how many times have you really written down the physical model to really hit the mathematical model? You simply say, oh, flat plate, you start del u by del x plus del v by del equal to 0 and start putting your boundary conditions. Boundary conditions, if you look at this, velocity conditions are fixed, not much can be done, either it is 0 or it takes the velocity conditions of the plate. But look at the thermal, we have now taken, we did not write it down, please write it down, isothermal plates, that it skipped my mind, both are isothermal. But if you look at the thermal part of it, you can put various kinds of boundary conditions on both the plates with various combinations, both isothermal, both non-isothermal, one isothermal, one non-isothermal, one with constant heat flux, both with constant heat flux, one adiabatic. How many kinds of boundary conditions you can have, combinations? Each one of those boundary conditions will give you a different solution for the same set of equations. any number of times I will be repeating this, the importance of formulating the problem rightly. Formulation of the problem correctly is 50% of the solution. Especially it is true, important rather, when you hit numerical techniques, when you use certain equations appear to give you the right solution, but they are really not the right solution because your numerical equivalents that you have written do not really simulate the mathematical equation that you have written. So whenever you write numerical use numerical methods, you should check for, most of the time you check for only for convergence. Stability criteria you have to develop, but third most important thing is consistency. Whether your finite difference or finite element representation of the partial differential equation or the ODE is consistent with that equation. Because of these round off errors and truncation errors, sometimes what you think is the right finite difference formulation will simply go off in a different direction, but give you a convergent stable solution. This has been experience of many people. It will not happen in every case, but there are situations where this happens, you should bear in mind. So formulation of the problem is extremely important, simplification is extremely important. I like this problem because in its entirety you can get this idea of what simplification. All solutions for Navier-Stokes equations is based on simplification. What is Prandtl's boundary layer? This is simplification. Here we did not invoke the boundary layer, not necessary. We have solved the entire Navier-Stokes equations in order to. Then you can of course add the heat transfer, what is it called, heat generation term you can add. We have kept a very important term in the energy equation, the viscous dissipation, we will see later. Now write down you have written the boundary conditions. So these 4 equations with the boundary condition, u equal to 0, v equal to 0, w equal to 0 at the wall, bottom wall, t equal to t naught at the bottom wall, u equal to u1 at the top wall, v equal to 0, w equal to 0 at the top wall. These are the boundary conditions. There are no initial conditions because we have taken as a steady state. Now let us proceed. Hope some of you have solved it, but let us go step by step. Solve the velocity equation. In any heat transfer problem, first you have to solve the velocity equation because you require that for the energy equation. In the case of forced convection, these are different. In the case of free convection, they have to be solved together. So what is the solution? D square u by dy square equal to 0, y equal to 0, u equal to 0, y equal to L, u equal to u1. So now this also tells you how, when you are actually applying a numerical technique to a partial differential equation, what are you doing actually? After putting in the finite difference for finite difference or finite element, then you go ahead with the solution point by point. Actually you are, I want you to fill up, you are dash the partial differential equation, you are dash doing this to the, no. When you get the solution, a differential equation, what should you do for you to get the solution? Huh? No, that is a numeric, that is you are directly jumping to discretization because you want to use a numerical method. Even after that, when you really solve, what does a PDE do? Partial differential equation, let us take t for example, dependent variable, it is a function of x, y, z and tau and all. What is the difference between a PDE and a finite difference equation? Finite difference equation of that PDE, what is the difference? What do you get when you solve these things in terms of the solution? Tell me. Where? In the other one? So you are, now I'll to save time, you are integrating the PDE you have to integrate. Now you do that here, that is what I am saying. D square u by dy square, twice you have to integrate, and 2 constants, the 2 boundary conditions you must have at y equal to 0, y equal to 12. Please, by looking at the equation you should be able to actually write it is nothing but u by u1 is equal to, so now we will go to what is this step now, solution, no, 4. Now we are actually going to the solution. So the momentum equation, that is the, I will say velocity profile is nothing but u by u1 equal to, please see, and what does this say, what kind of equation is this? now use the word whatever you used earlier, the solution now is linear. So plot this please in your physical model. What it says is at any given this is, let us say, x here. So here this value here is u1 and this is 0. Again I want you to appreciate this, such as originally what we thought was extremely non-linear, it is a linear profile basically. So one more point, V equal to 0 everywhere we have said, W equal to 0 everywhere, U is this profile. Now you come out with a name for this. What kind of a flow is this? It is not a potential flow, it is not a boundary layer flow. Okay. All the layers are, can you look at this? All the layer stream layers are to each other. In what fashion are they oriented to each other? It's parallel flow. V equal to 0, W equal to 0, it is simply a parallel flow, number 1. It is also a fully developed flow, it is not going to change, del U by del X equal to 0. So it is a parallel flow, it is a parallel plate geometry, it is okay, but you can have nonlinear velocity profile in parallel plates, as you will see later. And this happens only for dP by dx equal to 0, please see that. So therefore it is called a simple or plain Couette flow, and therefore you get a linear velocity profile, number 1. It is also called a parallel flow, as different from boundary layer flow. The streamlines are all parallel to each other. This is something again you get from this profile, very easy. The really exciting thing is go to the temperature profile. So write down the energy equation, d square T by dy square plus mu by k du by dy whole square equal to 0. Boundary conditions at y equal to 0, t equal to t naught, y equal to L, t equal to t1. We have not said what are the relative values of t naught and t1, leave it, let us see what happens later. Now we have to integrate this twice. I had yesterday asked you to do this, but some of you have not done. Go ahead and do it please. This actual procedure that you follow, this is a classical solution now, classical complete exact solution, no approximations. You get two constants, take 2 minutes. Give me an expression for t of y equal to what? T is function of only y now. Finished? Can you give me the terms? I will write down, tell me.
T0 plus T1
Plus
T1 into y by n.
T1 into, can
Y
you,
by n
y by n is it?
minus mu by k
Uh,
u square by k. First bracket y by n minus y by n whole square.
what is it? Minus is it?
No, y by n
Here.
bracket y by n minus y by n square.
Something else is missing here. Mu u square by 2k, yeah, this is okay. Is this minus or plus? Check it out, or you should. Did you all of you get this? This equation is important because you have to differentiate it later 2-3 times. Tell me. You know, some manipulation of this can be done. I am not sure. I will write. How many of you got this? Do not copy that. Don't. I am checking whether it is right or not wrong. But I will give you my the expression. You check it out. Maybe slight rearrangement will be all right. Please check this out. T naught, that is okay. Actually, this is also okay. Here, please see whether we would like to correct it. Please check whether something is missing there. And then this sign also. Check it out, please. We will reorganize it again later for something else. Something is missing there. Was it okay? Ty equal to T naught plus mu by 2k u1 square y by L y minus y square by L square plus T1 minus T naught y by L. Did you miss one term there? Check it out. How is it? Somebody tell me this second one is right, then I will proceed. Because you gave me the first answer, I am asking you. Everything is right except that T naught was missing. T1 y by L minus T naught, that just check it out, okay? Now you see a little bit. This is the equation which, please keep it. Give it a number. I don't know what is the number of this. And yesterday what was it? Can you give me a number? Okay, today I will give you this number. Now you see you have got a y by L. Without you are trying for it, you have got a non-dimensional distance now. Can you get a non-dimensional temperature difference by manipulating this? Just look at that expression. There is a T here, which is what we want. There is a T naught. There is a T1 minus T naught. So I can rewrite this expression as T of y minus T naught. Bring T1 minus T naught to the left hand side. Now you have a non-dimensional temperature difference. It is not non-dimensional temperature. It is non-dimensional temperature difference. Always non-dimensionalization makes things easier for various reasons. Now, so this is y by L, this is y by L plus this whole thing divided by see, now you have got a non-dimensional temperature difference, temperature in the non-dimensional form as a function of a non-dimensional distance, which is very nice. On its own it is coming out, slight manipulation, and as a function of the fluid, the viscosity, the velocity, the thermal conductivity. We will do a small further manipulation and see something else very important will come out, and then we will go further. Can you, okay, temperature difference is non-dimensionalized. This is non-dimensionalized, therefore one would think this term is non-dimensional. please write down what this term would be, mu u1 square by 2k T1 minus T0. Am I communicating here? Am I communicating, please? That term, I am saying T minus T0 by T1 minus T0 you have y by L. Why don't we put the other, see whether non-dimensionalization possible. What is that term? Mu u square by 2k is there and you have divided by T1 minus T0. How can you non-dimensionalize? What is it that you can do here? I will give you a hint. You will get a very well known non-dimensional number out of this by slight manipulation. You are jumping, fine, fine, we will get the Eckert, but a more familiar non-dimensional number, you have a mu, you have a k. How to get a Prandtl number there? Multiply, divide by Cp, and now you see what you are getting. Only now you get the Eckert number. So now you will see the non-dimensional temperature difference. Can you give me the second term here? T minus T0 by T1 minus T0 equal to y by L plus mu Cp by k is now Prandtl number. Then what else you have there? So you have mu Cp by k, half is there of course. You have u1 square, T1 minus T0 is there. You have multiplied and divided it by Cp. Now look at that Prandtl number, you know. Now you are coming out with a new non-dimensional number. You did not try for it. It is coming on its own with a slight manipulation. And what is that number? This number is the Eckert number. We did not plan to get this. We did not say we will get a Eckert number. Even when they did it first time, they did not plan for Eckert number. It was that name was given. That is a different matter later. But you see how from again and again I emphasize this, from very simple problem you are coming out with Prandtl number, you knew that of course. Eckert number is very new and it comes out because of u1. Look at the expression u1 square by Cp delta T. What is the physical significance of a Prandtl number? Mu Cp by k. What is the physical significance of the Eckert number? u1 square by Cp delta T. Cp delta T is a imposed temperature difference. So Cp is a imposed thermal energy kind of a thing. And what is u1 square? It is a kinetic energy. So kinetic energy divided by a imposed thermal energy form there, Cp into, actually it is a Cpt naught minus Cpt1. So there is a certain, in a problem, in this problem there is a certain energy in terms of Cpt that is now being related to the velocity of the plate. If the plate were stationary, it would not have come up. In fact, that would be 0 obviously. So a new number has come up now called Eckert. Some books give you the symbol as EC, some give you as the symbol E, you use as you like, but now you just change the final equation as y by L plus half Prandtl Eckert into y by L minus y square by L square. You do not have to do that, but this gives you a new, you can visually see the new non-dimensional number, and you also realize that it is important only when u1 is significant. u1 can be 0, then it is not significant. u1 can be very small value, it has its own role, but you also know it changes with u1 square. So from 5 meters per second u1 you go to 10, the effect is squared actually. So that means a small change in the velocity, finite change, will have a very that power law dependent effect on the Eckert number, which is nothing but the manifestation of the u1 square, the kinetic energy. If you go into the previous one here, this actually is much more, according to me, representative of the situation, mu u1 square. we are talking about viscous dissipation. If you look at only u1 square, it is kinetic energy, that is also right, but the real effect is the viscous dissipation is mu u1 square, and that can be, mu is already here in the Prandtl number, so you can try to give it a physical significance. This is extremely important. Why do we do all this? We would like to know the temperature difference. By the way, suppose you have u1 equal to 0 here, what is the temperature profile? Linear, same thing. In fact, the velocity profile is linear, temperature profile is linear when u equal to 0, that means it is simply conduction, it is just conduction that is happening. The moment you start adding u1, convection is coming into picture, the profile is becoming nonlinear. This is a nonlinear term now, second term is u1 squared is being introduced. Now this is the temperature profile. After getting the temperature profile in a convection problem, what is it that we want to do? Find out what is the heat transfer at the top plate, what is the heat transfer at the bottom plate, get the expression. How do we do this? Therefore, you should first get, now I will say this is step whatever, now I have lost track of this, heat transfer Q, I will say flux equal to minus K dt, I can easily write dt by dy, there is no problem, not necessarily del t by del y. This is a general expression. If I put Q0 here, this is the wall, so I have to put dt by dy at y equal to 0, and flux at L at the top plate is minus K dt by dy at y equal to L. Can you get two simple expressions? First get dt by dy and get two expressions, please. That will complete this part of the Couette problem. There are two more important things which I want to refer to. Get a general expression for dt by dy from the T equation. You know how to do this, isn't it? What I will do, you do it, it will take some time. I will give you the expressions, check it out, but I want you to do it separately. Q0 double dash, the heat transfer at the wall, this is equal to minus mu u1 square by 2K, 2L, sorry, minus K by L TL minus T naught, T1 minus T naught, minus mu u1 square by 2L minus K by L T1 minus T naught, and the heat transfer at the top wall is plus mu 1 square by 2L minus please check it out. So you get the temperature profile, then take dt by dy at 0 multiply by K minus K, you get the heat transfer at the bottom wall, and then heat transfer at the top wall minus K dt by dy at y equal to L. This is all fine. These are all equations, but you have to have numbers finally. So what I will do, I will give you a very simple problem. I want all of you to write a simple program and now study this solution for the effect of various variables here. Tell me, looking at these expressions, what are the important variables that affect the heat transfer? Number 1, okay, we will give the velocity. So all other conditions being the same, u1 controls the heat transfer, influences the heat transfer. Then what else? Suppose I keep u1 constant. Fluid, Prandtl number. Okay, then
temperature difference.
Temperature difference, right? course you have to say L, but we will fix L now. I want you to do the following, please. Take a problem. I want you to write a small program for this. We have these two plates, distance small. We have never talked about what is L actually. Let us take this L equal to 3 millimeters, and this is U1. Please switch off your mobiles, please. 10 meters per second. Yeah, we will see the Prandtl number here. This is at 10 degrees. Yeah, T0 10, T1 30. Is everything there? Prandtl number. Now, I want you to do this. Take air here, Prandtl number. Take water. Take what is referred to as engine oil. Different kinds of oil are there. Fuel oil, engine oil. That gives the Prandtl number. With these conditions, please get the temperature profile, but basically the heat transfers at the two walls. Find out what is the effect of Prandtl number. Then in the same program, please change this U1 up to 100 meters per second or so in 10 meters per second intervals. Find out what is the effect of this velocity. Okay. Now, keep it at 10 meters per second, change the bottom temperature T0, take 5 degrees centigrade and 50 degrees centigrade. You get the point what I am trying to do here. Prandtl number, 3 Prandtl numbers: air, water and oil. Higher velocities, 10 meters per second is very small. Temperature, you see what I have done. The first problem I have given is 10 degrees centigrade, keeping that at 30. Why I have given you 5 and 50? Okay. If I take 50 here, what is the difference between this problem and that problem? This is 30 and 10, so T1 is greater than T0. Actually what you could do, you could also take 30 degrees, T1 equal to T0 and then T0 greater than T1. See the difference in heat transfers. But actually there is a very important application of this, and therefore another factor is extremely important for us to calculate. The moment there is a non-linearity in the temperature profile, can you visualize another factor which may come into picture? Another kind of a temperature within the fluid. By the way, please understand, all this temperature profile is for the fluid. Plate temperatures are fixed. If there is a non-linearity, what would you like to look at as a means of as a way of understanding the problem? Linear, you know how it is. Now there is a non-linear thing. Whenever there is a non-linearity, we would like to find out one particular. I don't know whether I am able to communicate this question properly. You want to look at something else in terms of the temperature profile. How does it? Will it continuously non-linearly vary in one direction? I am trying to give a hint. Or could there be a, in the curve, what do you expect? You have 10 degrees at the bottom and 30 at the top. linear profile you can easily see how it is. How would be the non-linear profile? I will come to that, you have to plot it, then only maybe understand. Okay, maybe I am not able to communicate, let me assume I am not able to communicate the problem, I will state it. What is the maximum temperature in the fluid? Find it out. Find out if there were to be maximum temperature, because it is a nonlinear problem. The answer is actually my reason for asking you to do this. How do you find out whether there is a maximum or a minimum? What do you do to the equation? Huh? What? Differentiate what? So dt by dy should be what? Find out if there is a dt by dy equal to 0 at what condition. How do you find out whether it is a maximum or a minimum? Do that. See if there is a maximum, and if it is there, find out if there is a maximum, what would you like to find out? First of all, find out whether there is a maximum. If there is a maximum, what is the next question that should arise in your mind? Huh? Okay, but something else related to this? Huh? Please find this out, this is very important. And therefore, I want you to say what is the T maximum for air, for water, for oil. Oils can be anything, Prandtl number from 1000 to 50,000. If you want, you can check it out, but take any 1 or 2 Prandtl numbers, it is okay. And please write a small program and plot all these things. We go back to the temperature profile. How do we plot? Plot the temperature profile. What should be the ordinate and the abscissa? What can be? Look at the physical problem and how do you want the profile to be plotted? What should be the abscissa? What should be the ordinate? That is fine. So where do you want theta? Where do you want to? Looking at the problem, which would be okay for you? So you please plot what will be the maximum value of y by L? Of course, this is 0. What is the maximum value of y by L? What is this? What is the linear profile? If there is no u1, u1 is 0, static plate, how will this be? Here to, where will it go there? What I want you to do is really plot. When I say u1 equal to 0, look at this expression please. Theta, if this is theta, if we want to refer to it, theta equal to y by L. That profile is for second term being absent. The moment I bring in u1, that means Eckert is coming into picture. Tell me, give me the effect of Prandtl-Eckert number. That will give the effect of the u1, more importantly viscous dissipation. What numbers can it take? Huh? You do not know, you can assume now at this point in time. I am going to suggest to you, use this expression. Now this is a very nice non-dimensional expression, it came off just like that. Plot y by L and this for various Prandtl-Eckert numbers. Prandtl-Eckert numbers and I want to convey to you, unless you plot it, you will not understand what I want to talk about in the next class. Please do this. Not only plot it, think about it, what is happening. I have to still bring out two important aspects of this whole problem. We will do it on Monday, no problem. I am not in a hurry. I want you to understand this, especially 1, 2, 3 concepts will come out of this, which you can then relate it to normal convection. So, please plot this. Y by L plotting is no problem, it is the same thing. Y by L and theta are the same, u by u1 equal to y by L, theta equal to y by L. So, there is no problem, but for varying Prandtl-Eckert number, make sure that is when you do that you will know there is a maximum. Now, I am giving you actually the answer, but I want you to do that. There is a maximum, find out where that maximum is, why, think about it. That is one aspect of the solution. If a maximum comes into picture, what is the effect of this on the heat transfer? Not the rate, heat transfer direction at the 2 plates. We have, when we said how to plot, you said something, when I asked what is the maximum temperature, you said T1. You will find it is not T1, it is something different. It is T1 if there is no U1. Because of U1 something is happening, that something is there is a maximum which occurs. I am giving you that answer, find it out at some location. But then what is the effect of that maximum coming into, first of all why and what is the effect? That will affect, gentlemen, the direction of heat transfer itself. This is extremely important point I want to make little bit more force in the next class, but for that I want you to plot the theta with respect to Prandtl-Eckert. Also, it is not simply Eckert, it is Prandtl-Eckert. When you then fix up a Prandtl-Eckert, numbers will change, that is different, but give a number to Prandtl-Eckert as 1, 2, 3, 4, 5, 6, 7, 8. In particular, tell me what happens at Prandtl-Eckert equal to 2. Study that. Also therefore find out what happens after Prandtl-Eckert equal to 2. What happens means what happens to the heat transfer, that is what I am looking at. You will find very new information coming out of this. This is very extremely important. I will ask you something else now before I leave you. Look at the Couette problem. What does that, look at that, please look at that. There is a bottom plate fixed, there is a gap, there is a top plate which is moving, there is a temperature here, there is U equal to 0, U equal to U1. What does this physical model remind you of, which you are more familiar with? You will be, that is because you have not thought, which is okay, no problem. We have said there is a plate. Suppose there is no plate, but there is a velocity. What would that problem boil down to? Look at the physical picture, look at the boundary conditions, Baba. Huh? Huh? Flat plate, okay. Flat plate, what is the flow there? What is the type of flow? Do not simply say flat plate, add something to that. What type of a flow on the flat plate? Sometimes you have to give the teacher the answer that he wants. But in different ways we can discuss about it. This point you have not thought of so far, I am making you think, requesting you to think rather. You are right, but flat plate, huh? Boundary layer flow. Do not simply say laminar, that is also correct. That is why I want the right words to come. Look at this problem, Couette problem, you thought it is all restricted, but one of the takeaways from the Couette flow is this can be related to a boundary layer flow, very simple. Bottom plate fixed, y equal to 0, u equal to 0, t equal to tw. Y equal to L is y equal to delta, u equal to u infinity, whatever that is, t equal to t infinity. with one small qualification. What could that? You are right. Now you can write a sketch of the boundary layer flow and compare these two. Where will this Couette flow situation will be really applicable in a boundary layer flow? In what zone? Or tell me where it is not applicable. Huh? Delta is always varying. Delta is a function. Delta is y by x root Reynolds x. Huh? Near the entry it is not valid. I say I wanted that word. That's actually now the Couette flow is nothing but a representation of a fully developed boundary layer flow. Fully developed, I would say, on a flat plate still, but you can extend it to the pipe flows later, where after that nothing is changing. It is a constant. You can it varies as delta by x is y by x root Reynolds x power half. It varies, but as you go along half, the rate reduces. So away from the leading edge, the flow is very similar to Couette flow. Once you appreciate this, the effect of viscous dissipation you can actually superimpose upon the boundary layer flow, post convection boundary flow, and therefore any information that comes out of it is just it has to be modified for a regular flat plate flow. This is one of the major takeaways from looking at a Couette flow in some detail. We could have done it by I could have given you the equations and then you say solve it, you would solve it, but I want you to please think about these things. So that is another takeaway. We will stop here now. Monday we will meet. I will draw the profiles, solve this problem. I know you have other subjects, but also please do this. You have a what is it? Quiz. This is a quiz week, but do this as much as possible. At least for one Prandtl number, especially for oil you do. I am giving just a hint. You know why I am saying this? This problem. Okay, tell me in machines, in mechanical equipment, where would you? I have given you a hint actually. Where would you apply this? Especially therefore, look at the size of 3 millimeters that we have taken. This is a journal bearing problem actually. But where is journal bearing problem? How can U1 go to infinity? I mean, a constant U1, a plate moving at U1, actually that is replaced by the journal. So that's you can take it as a flat plate moving continuously, and then there is a bearing. In between is, now tell me why T max is important. Not simply for you to do some calculations here and say, sir, I got T max. Now related to journal bearing problem, why is T max important? That is why I asked you to do for oil. Journal bearing, if I put oil, what is that? Why do I put the oil? Huh? What is the word used for that? Lubrication. And for you are putting oil, why? It has a certain kind of what? Viscosity. Now how does temperature affect viscosity? Find out. You have to maintain the temperatures properly for the oil film for you to have that lubrication effect. Lubrication will fail under these conditions. So find out what is T max. Now you see this Couette problem has a practical application, although not a very great. It is important actually, but it is not earth shattering application, but it is a very important application. You will know how to formulate the problem, how to make simplifications, how to make it the simplest of equations in convection, but how much information you can get out of it. Especially in the next class, after you draw the temperature profiles, we will discuss a little bit further and see something very interesting that is happening there. Thank you.